Thank you, Chairman. So, my name is Toru Ikeda. I came from Kagoshima University in South area of Japan. So this is the contents of this presentation. First of all, I talk about the background and objectives of this presentation. And next is theory. And after that, I show you some numerical analysis. And finally, I talk about the conclusion. So this is the background and the objectives of this study. As you know, the many microstructures are built up using many different materials like this. And these structures have many bonded corners like this. And the bonded interfacial corners are stress singularity points. So the fracture will occur from these stress singularity points. So it's important to investigate the stress singularity around the bonded corners to evaluate the fracture from the bonded corners. And in our previous study, we proposed a new numerical method to calculate the scalar parameters, Cm of the asymptotic solution of the singular stress around the sharp 3D corners like this. So the asymptotic solution is expressed like this. So I told about this later. So in this study, we propose the definition of stress intensity factors for a sharp 3D jointed corner. This definition includes the definition of other many definitions like this. So this time we proposed unified stress intensity factors of a sharp 3D interfacial corner between dissimilar anisotropic materials. This definition includes also the stress intensity factors for two-dimensional interfacial corner. And also it includes the interfacial crack between dissimilar isotropic materials and also between dissimilar isotropic materials. And it includes the stress intensity factors of the crack in homogeneous materials, so usual crack. So the asymptotic solutions around the sharp 3D corner is expressed as these equations. There's a stress and displacement. And in these equations, K is a material number, and R is the distance from a corner. And N is a number of singular evaluations, and the lambda is singular eigenvalues. And also the F and G are eigenfunctions. And we can obtain these eigenvalues and eigenfunctions obtained by the materials and the so only by the combinations of the materials and bonded angles. And only the scalar parameters Cm is depend on the boundary conditions at far field, so we can obtain using the H integral. So first of all, we analyzed lambda and F and M using the special finite element method for eigenanalysis. And after that, step 2, we analyzed Cm, scalar parameters, using the usual finite element method for stress analysis. And finally, we obtained the scalar parameters using H integral. So we obtain the eigenvalues and eigenvectors using the eigenanalysis of special finite element method like these figures. So this method is proposed by Peggy et al. So we, using a finite element method, obtained these eigen equations. And after that, we modified this equation to this standard eigen equation. And we can obtain the eigenvalues and the eigenfunctions by these finite element analysis. After that, we obtain the scalar parameters Cm using the another numerical analysis. based on the Betty's reciprocal theorem. This is Betty's reciprocal theorem, like this. And we modified these equations like this. We obtain the H integral. If we, and in these equations, sigma and U is stress and displacement for the target problem. And UI star and sigma ij star is reference problem. So if we choose the reference problem reasonably, we can obtain the scalar parameters from these H integrals. This is usual mechanical problem, and this one is including the sum mechanical problem. So after that, we define the stress intensity factors. So this is the asymptotic solutions, and it's so detail of the asymptotic solutions. So in this case, we obtain these three components of the stress, and these eigenfunctions can be expressed by this F1, F2, F3. This is F1, F2, F3, and finally, so we show like this lambda. And we can define the stress intensity factor for the sharp 3D corner like these equations. And in our previous study, so we proposed the stress intensity factors for two-dimensional corner like this. And in this time, so we propose these definitions for the stress intensity factors for the sharp 3D corner. And let me show you some numerical examples. This example is a sharp corner between the Fe and aluminum, and the obtained eigenvalues we can obtain these three eigenvalues. And also we can obtain the scalar parameters like this. And also this is one of the eigenfunction. And this table shows the stress intensity factor for this problem. So using these stress intensity factors, we can obtain the distribution of the stress intensity factor on this interface. So this is the result. We can show the distribution of the stress intensity factors on the interface between Fe and aluminum like this. So in this case, the case is a summer problem. So the shear stress is the most important. So we focused on these figures. This figure shows the squared means of K2 and K3. And in this case, K1 and K2 squared, K2 squared and K3 squared is symmetrical. So it means that maybe the edge along the x1 axis and x2 axis is the largest. So we can predict the, in this case, so crack occurred from the corner and it expand along these two edges. And the next example is the anisotropic one. So this case is one is the silicon and zinc oxide, both the asymptotic anisotropic materials like this. So in this case, we can obtain the eigenvalues and scalar parameters like this. Also, we can obtain the stress intensity factors for these angles. So also we can obtain the distribution of the all angles on the interface face. In this case, we focused on the squared means of K2 and K3. In this case, this one is takes the maximum at the 90 centigrade. So 90 centigrade is along to the x2 axis. It means we can predict the crack extend to this along to the x2 axis first. And next one is the embedded example. As you can see, the copper is embedded in the epoxy resin, and we change the so temperature minus 100 centigrade, and we obtain eigenvalues, these three. And also we can obtain the scale parameters like this, and we obtain the stress intensity factor for these angles. Also, we can obtain another angles. So we can obtain the distribution of the stress intensity factor on the this copper. So in this case, so we only focused on the upper surface of the copper, and this is the result. So we can obtain the distribution of the stress intensity factors for K1, K2, K3, and the squared means of K2 and K3. Also, we focused on this case, so squared means of K2 and K3. In this case, this value takes the 3 peaks. So in this case, it's suggesting the crack extend along these 3 peaks. So both edge and the center 45 degrees directions. Okay, so let me conclude this presentation. First of all, so we propose the unified definition of stress intensity factors for sharp 3D jointed corner. And then we propose stress intensity factors for sharp 3D jointed corner. Includes the definition of stress intensity factors for a 3-dimensional jointed corner, also a 2-dimensional interfacial crack, and the interfacial crack in between the anisotropic material, also crack in a homogeneous material. And asymmetric solution with proposed stress intensity factors can describe the singular stresses field around sharp 3D jointed corner. So I can say the proposed stress intensity factors for sharp 3D dimensional jointed corner can predict the direction of the crack extension from the corner. Thank you for your attention.